continue. Okay, let me open the table of content first. Alright. Previously, we are on chapter 18, patching introduction. Let me open that first. And then, if I remember correctly, we are on this one, section 18.5. Okay, let me take a look at that. Right, we are in this section. Okay, I'm still not sure about this figure 18.7. Let me read again. The entire process for the first 5 loop iteration is depicted in figure 18.7, page 11. The bottommost graph shows the instruction memory reference on the y-axis in black. The bottommost graph is in black. Is this it? Okay. Instruction memory reference. Okay. With virtual address on the left and the actual address on the right. This one virtual address, I assume, and this one is the physical address. And this is graph for the code or instruction. Okay. Finally, the topmost graph shows page table memory access in light gray. I think this one page table, the gray, light gray, right? Yeah, light gray. Just physical as the page table in this example resides in physical memory. Oh, okay. So this is the physical memory or physical address, I guess. And then I assume this is the entry. Maybe something like that. The x-axis for the entire trace shows memory access across the first 5 iterations of the loop. There are 10 memory access per loop. 10 memory access per loop, which include 4 instruction fetch, 1 explicit update of memory, and 5 page table access to translate those 4 fetch and 1 explicit update. There are 10 memory access per loop, 10 memory access per loop. Oh, because we have, what is it called, around 2 memory reference, I guess. Fetching the page table entry, and then we are fetching the, what is it called, the data in the physical address. That's why there is what is it called, 10 memory access per loop on the first 5 iteration of the loop. So what is it called, 1 memory access to get the page table entry, and another memory access to access the actual, what is it called, the actual data in the physical address. Okay, something like that. That's why it is 10 memory. One iteration need 2 memory access. So when we have 5 iteration, we got 10 memory access here. Per loop. Wait, is per loop mean per iteration, or I'm assuming it's just the loop, like for example, if we do this, right, this is one loop, I assume, and inside this we are doing the iteration in this loop. So yeah, maybe something like that. So inside the loop we have specific iteration, okay, which include for instruction fetch, 1 explicit update of memory, and 5 page table access to translate those, 4 instructs for fetch, and 1 explicit update. Oh, wait a minute. Is it 10 memory access per iteration? I don't think so, I guess. Okay, let me check this. Okay, maybe something like this. Right, for instruction, and then wait a minute, for instruction fetch, and 1 explicit update of memory. Yeah, in this case we didn't update the memory, I guess. Oh, I mean, maybe this one. We are adding 0 to the array index register here. Alright. Okay, so this one is the update process, and this one is what is it called? Oh, for instruction fetch. So we fetch all of this instruction, right? And then what is it called? Execute the update memory. This one. Wait, let me demote that, I guess. Fetch instruction. Okay. Increment. Compare. Jump if not equal. Something like this. And then one explicit update, one update, execute update instruction, this one, then memory access, one update instruction, 5 bits table access to translate those 4 fetch. 5 bits table access. Oh. Okay. So let's say we, in this 5 iteration, we are accessing the 5 table entry, 5 bits table entry access, and each of the access we do this, maybe something like that, and each access do this. But I don't think that is correct. One page table access to translate those 4 fetch. I mean, if that is the case, it is more than 10 memory access. We are accessing memory in this one, also this one. Maybe not this one. But we are comparing the value of the index, right? This AAX is the array index. So maybe we also access the memory in this one. See if you can make sense of the pattern that show up in this visualization. Yeah, that is the challenge here. 1, 2, 3, 4. Okay. 1, 2, 3, 4. Okay. Wait, 1, 2, 3, 4, 4. This one is 16, and this one 20. So page table entry 1 is 20. The topmost graph show page table memory access in light gray. Yeah, if I'm still not sure about this one. Five page table access to translate those 4 fetch and 1 explicit update. And then why this one is 10 memory access per loop. I mean, we fetch the instruction, right? And then we are updating the content in the memory. So maybe something like this. With page table. So git one update instruction access to get the data. This is that it? I mean, we fetch the instruction first, right? And then five table entry access to get the address, maybe something like this. And then after that we execute the update instruction. So maybe the 5 memory access is from this one to access the physical address or something like that. And then we yeah, wait a minute. So this one is 5 memory access. And this one is 4 memory access. This one is 1 memory access. Maybe something like that. That's why it is 10 memory access per loop. So every loop, or maybe every iteration, we fetch the instruction. But wait, I don't think we fetch the instruction in each iteration. But we fetch this instruction once, and then doing this again. So maybe when what is it called? When it is not 5 iteration, right? Let's say 10 iteration, it becomes something like this. So 10 bits. Okay, so 10 bits memory access, right? And then what is it called? Its update instruction, it is this one, also accessing the memory. So if it is 10 iteration, it is not 10 memory access, but maybe 15, something like that. Okay, maybe that is my hypothesis for now, I guess. But yeah, it's kind of confusing for me. 5 bit stable access to translate those 4 fetch. Right. I'm assuming translate in this one is to change the, what is it called? The register here. And we got the information of this register in the page table entry. Maybe something like that. Okay. Maybe that's what it means, 10 memory access per loop. At least in this case, the loop, we assume only the first 5 iteration. Okay. But why is it 20 in the page? Page table entry 1. Yeah, this one is 4, right? But why this one is 3 and this one is 1? And why the page table entry 39? Okay, wait a minute. Let me check. Okay. There is the array itself. Its size is 4000 byte. Okay. 1000 integer. And we assume that it resides at virtual memory. Okay. Not including the last byte. Alright. The virtual page for this decimal range are this one, virtual page number 39 until 42. So this is the page table entry to store the, what is it called? To store the data, I guess. We are having 5 iteration. So this one have 5 data in this entry. And that make me curious. We have 1, 2, 3, 4. Did each what is it called? Did each table, page table entry can hold multiple address, maybe something like that. Can hold multiple address. That's why we have the offset, right? For this page number or page table entry 39, if the total size is 4000 byte, I assume it's page table entry here can hold maybe 1000 byte, something like that. So the page table entry or virtual page number 39 can hold 1000 byte. Virtual page number 40 can hold 1000 byte again, and so on. Maybe something like that. And because we only doing 5 iteration, we are only filling up the page table entry 39 with 5 data or address, maybe something like that. With 5 data in the page table entry 39. But yeah, I'm still not sure about this one. Page table entry 1. Let me check. Okay, I think this one. Virtual page number 1. As virtual page number 0 is the first page. Okay. As for its content, there are just a few virtual pages we need to worry about having map for this example. First, there is the virtual page the code live on. Because the page size is 1 kilobyte, virtual address 1024 reside on the second page of the virtual address space. Okay, the virtual page number 1. Okay, so does this mean this page table entry 1 is where the code live? So we are fetching the instruction, the for instruction here. Maybe something like that. So we update the 0 index of the array. Write this one. Update 0 index of the array. And then increment, compare back to this instruction again. this one increment, this one I think compare, and this one jump to the previous instruction, and then this one updating again. Maybe something like that. Let me check. Stable entry 1. What is it? Yeah, move. And then increment, compare, jump if not equal, and then update again. This one keep going. 1, 2, 3, 4. 1, 2, 3, 4, right? We are updating 5 times. 1, 2, 1, 2, 3, 4, 5. We are updating 5 times. And then the next one, right? This 3, the last 3. What is it called? The last 3 point here is increment again, the increment the index, right? And then compare. For this case, we only take a look at the first 5 iterations. So the assumption is that we only have 5 iterations in the loop. So comparing 5 with the current index, and if it is equal or more than the current index, we are not jumping again, I guess. This one increment 1. Okay, this is 0, right? The what is it called? Index 0, and then this one index 1, this one index 2, this one index 3, index 4, I guess, and this one index 5. And because we start on the 0 index, right, the what is it called? The last index is actually n-1, which is this one, index 4. And then so when we hit the index 5, we compare that with the maximum index that we provide, which is 5. So it is equal, right? Not less than the index, not less than 5. So we evaluate this and not jump back to this one. I'm assuming JNE in here means jump if not equal, but the thing is that it is equal, so the result in this one is equal, so we didn't jump to this line anymore. Maybe something like that. Okay. But then what is the correlation with this one? Interesting. Like, what is the correlation of 5 iteration of the loop and the 10 memory access with this page table entry 1? I'm assuming that we only access this for... Okay, yeah, maybe after accessing the instruction, we are only executing the instruction here, not accessing the memory again, except when we update the value using this one. Right. Okay. So this is for excuse me, for instruction fetch or for memory access, and then one update of memory, but because what is it called? But because we are doing that 5 times, so every time we update the memory, is it also considered in this 10 memory access? Fetch for instruction, okay. Let me think. 5 memory access. To get the address to store data, something like that. Execute one update instruction. I mean, if you are doing 5 iteration, right, we are updating 5 times. So maybe maybe 10 memory access in here means per iteration. this one is just one iteration, but we are accessing 5-page table entry, 5-page table. I'm still not sure about this one. 5-page table access to translate those 4 fetch and 1 explicit update. So I assume one, what is it called? 1-page table access is having this 4 fetch and 1 explicit update, maybe something like that. For fetch and 1 update. One update executed, maybe something like this. And if it is and if it is 5-page table access, isn't we just multiply that five-page table access multiply by 4 fetch plus 1 update. So what this mean? 10 memory access parallel loop. Yeah, I'm still not sure about this one, but I can kind of see how this page table entry works, I guess. And this one we are accessing the instruction. Is accessing the instruction also considering the memory access, or we just fetch the 4 instruction here at once? And then what is it called? And then just mapping the element in the instruction to the memory address from page table entry. Maybe. So if that's the case, we fetch the instruction once, right? And then we are updating here. So if we have 5 table access, that means 5 update execute, but then we only have 9. Not 10. Yeah, maybe something like this. this. I'm still confused by this statement. Where do we get the 10 memory access? Okay. See if you can make sense of the pattern that show up in this visualization. In particular, what will change as the loop continues to run? Okay. What will change as the loop continues to run beyond this first 5 iterations? Which new memory location will be accessed? Beyond the first 5 iterations, well, we might also use another page table entry like this one, page table entry 40, page table entry 41, and page table entry 42. As for this one, well, we keep accessing what is it called? The instruction, I guess, is gonna keep going. So maybe something like that will change as the loop continues. Which new memory location will be accessed? The page table 40, page table entry 41, page table entry 40, page table entry 41, and page table entry 42 will be accessed. Only half of it. Can you figure it out? I mean, only a little bit. Yeah, I'm still not sure about this one. Maybe I will try to analyze this off stream. Okay. This has just been the simplest of example, right? Only a few lines of C code, and yet you might already be able to sense the complexity of understanding the actual memory behavior of real application, right? It's kind of complex, I guess, but this is the simplest of the example. Okay, don't worry, it definitely gets worse. I'm not sure if that is encouraging. It definitely gets worse, because the mechanism we are about to introduce only complicate this already complex machinery. Sorry. Okay, let me read the footnote first. We are not really sorry. Oh my god. I like how the author throwing this out, guys. We are not really sorry, but we are sorry about not being sorry. If that makes sense. Okay, well, summary. We have introduced the concept of batching as a solution to our challenge of virtualizing memory. Batching has many advantages over previous approach, such as segmentation. First, it does not lead to external fragmentation. Well, I assume it is still gonna lead to external fragmentation, but maybe not as bad as the variable size segmentation here, as patching by design divides memory into fixed size unit. Second, it is quite flexible, enabling the sparse use of virtual address space. However, implementing patching support without care will lead to a slower machine with many extra memory access to access the page table, as well as memory waste. Right, this is the two problem that in the previous section mentioned. Two real problem here that we must solve. The first one is the slowness because of what is it called? Where is it? Because of extra memory access to access the page table and memory waste. It means that what is it called? We have unused memory, something like that. With memory filled with page table instead of useful application data. We will thus have to think a little harder to come up with a patching system that not only works, but works well. The next two chapters, fortunately, will show us how to do so. Alright, okay, so this is the reference. One level storage system. Okay. The Atlas pioneered the idea of dividing memory into fixed size pages, and in many sense was an early form of the memory management ideas we see in modern computer system. Okay, Intel 64 and IA32 architecture software developer manual. I'm assuming IA in this case mean what is it called? Instruction architecture, maybe something like that. I'm not sure yet. Architecture software developer manual. In particular, pay attention to volume 30A, System Programming Guide Part 1, and volume 30B, System Programming Guide Part 2. Okay. The Manchester Mark I and Atlas, a historical perspective. This paper is a good retrospective of some of the history of the development of some important computer system. As we sometimes forget in the United States, I guess, or what is US stand for here? Many of this new IT came from overseas. Oh, maybe this one means United States, the US. Many of these new ideas came from overseas. Okay, and then there is this homework simulation. Let's try this homework simulation on the next section. On the next session, I mean. So that's it for now. Thank you for watching and see you next time. Bye bye.